Let's do this thing. More implicit differentiation. Woo woo! Okay, so for what values of x will the curve x cubed plus y cubed equal to 4x plus 1 have a horizontal tangent? Not only do we get to use implicit differentiation, but we also get to solve a problem. After that, we get to think further. Woo! Horizontal tangent, remember, is when the slope of the tangent is 0. Slope of the tangent is also known as derivative. So I need to set dy dx equal to 0. To do that, I need to find dy dx, or we do. So I'm going to take x cubed plus y cubed is equal to 4xy plus 1 and find the derivative. The derivative of x cubed is just 3x squared. And the derivative of y cubed, similarly, is 3y squared. But y is its own function, which means we need to take times the derivative of the inside, which it would be dy dx. You know, because chain rule. Wow. Over here, if you're like, why didn't we do the chain rule on this one? We did it. It's just the 3x squared times 1 dx dx, which we don't have to write. So dy dx is equal to 4xy, yeah, product rule, first, times the derivative of the second. So 4x times dy dx plus the second, so the second term is just y, times the derivative of the first. The derivative of 4x is just 4. And this is where people mess this one up often. Don't let this be you. Don't volunteer as tribute. The derivative of 1 is just 0, so you don't have to write that down. The next step is you want to get anything with the dy dx on the one side, everything else on the other side. So I'm going to subtract this 4x dy dx. And then on the other side, I'm going to subtract 3x squared from both sides, and I get to keep the 4y. Your next step is to factor, so dy dx, factor out 3y squared minus 4x, and then I have negative 3x squared plus 4y. The next step, 3y squared minus 4x. Boom. So now I know my derivative. And now I need to set my derivative equal to 0 because I want to know when does this have a horizontal tangent. So setting my derivative equal to 0. The thing about this is you can do one of two things. You can either multiply both sides by 3y squared minus 4x and think about it that way. Or you can think, well, the derivative, if this is a numerator over a denominator, the only thing that has to be equal to 0 would be the numerator, because 0 divided by anything is 0, except for 0, but the bottom's not going to be 0 at the same time. So what I do is I set the numerator equal to 0. And this one says for what values of x will this have a horizontal tangent. So now I need to do a little bit more work. And now I'm saying, okay, well, I've got negative 3x squared plus 4y is equal to 0. How in the heck do we do this? Well, why don't we just start by solving for y? So I added 3x squared on both sides, and I get 3/4 x squared is equal to y. You're like, okay, that doesn't help me too much. But it does if you've got a crazy system of equations. So we've got y is equal to 3/4 x squared. This isn't the only function I'm dealing with. Well, technically not a function since it's implicitly defined. I can go back up to this first one, and I can say x cubed plus, instead of y, I'm going to write in 3/4 x squared. I don't know why I'm writing so little. Cubed is equal to 4x 3/4. Oh, that was terrible. I'm making it worse. This is a 3/4 x squared. And I'm going to simplify a little bit. So I've got x cubed plus 3/4 cubed. So 3 cubed, it would be 27. 4 cubed is 64. X squared cubed would be like x squared times x squared times x squared, which would also be known as x to the 6th. I multiply an exponent to an exponent, I multiply. Goes over here, I'm going to take 3/4 times 4, so I get 3x cubed. Okay, and then you're like, well, this is still really gross. What do I do then? Oh, and I forgot something. Don't forget the plus 1. It's like you're going to a wedding or inviting people. Don't forget the plus 1. No, that's not the same thing. This is just about math. Okay, so we're doing all of this work, and really, at this point, I've got only x's in my problems, and I really could have done it up here also. This is where you want a calculator. And if you were worried and you were thinking, oh, I'm going to mess it up if I try to do these, you could have put this in your calculator. It just requires more parentheses. So go to y equals, I have some other stuff in there. In y1, you want to put whatever's on the left and then whatever's on the right in y2. And then what we're going to do is find the intersection of these values. So I've got x cubed plus 27 over 64 x to the 6th. And then it's equal to, so in my second, in my y2, I'm going to write 3x cubed plus 1. And now I'm going to graph this, and I'm actually going to check my window first to see what it is. So if I push zoom 6, this will get me to a standard viewing window, like -10 to 10 for x's and y's. Okay, so I can see something's happening right around here a little bit. And so I'm going to decrease my x values a little bit just so I can see this. So I'm going to go to window, and I'm going to change my x min to -5, my x max to 5, just to zoom in a little bit, because what I want to see is the point of intersection. And it looks like my intersection's happening. My second intersection point is a little bit higher, so I'm going to change my y value just a little bit, maybe 15. Just a little bit of a glare, sorry about that. Okay, so I'm getting pretty close. I think I can see it up here. We'll check in a second. I'll be able to tell for sure. So what I'm going to do is find the intersection. So to do that, I find second calc. I go down to intersect, which is number 5. It's going to say first curve, and I can see at the top which curve it's on. So it's on my y1. I'm going to push enter. It goes to my second curve, and I can see it at the top. It's y2. I push enter again. So this guess, I don't actually have to guess, but when I move my cursor left or right, you see how my cursor is pretty close to this intersection point down here? The guess just gets you close to one of the intersection points. So use your cursor left and right to go closer to one intersection point or the other. So in this, I would get x is equal to, this is my final answer in this, so I can round this to 3 decimal places or truncate, meaning I can close this off. So -0.769. So I decided to truncate. If you decided to round, you would have to write -0.770. Either one is fine. And then the other value, so I can calculate intersect. I still push enter, but when I guess, I need to use my right cursor until I get closer. There we go. You can see I'm closer to this intersection point now. I'm going to push enter. And I can see I'm at x is equal to 1.732. This one rounding or truncating, you would get the same thing. So for what values of x will the curve have a horizontal tangent? I did that. Show your work and explain your thinking. So I'm going to say, I showed all my work, which was good. I will say the curve x cubed plus y cubed is equal to 4xy plus 1. We will have a horizontal tangent when dy dx, so when the slope of the tangent equals 0. And that's it. We did it. Looks so awesome. In the next one, it says, in terms of y, describe the values of x, which x cubed plus y cubed is equal to 4xy plus 1. So the same thing as we had up here. We'll have a vertical tangent. So we already know that this derivative from up above, dy dx, was -3x squared plus 4y over 3y squared minus 4x. So if we think about what a vertical tangent was, we can think back to actually last lesson when you learned about this, where we said, okay, well, I can see at the point 8, -2, there was a vertical tangent. If we looked at 8, -2, I could saw does not exist for my slope, which is fine. But I can also see that I had a rise of a number and my run was 0. That's going to happen every time. So any vertical tangents, I set my denominator equal to 0. So I'm going to say for the curve, so I'm explaining first. You could do it at the beginning or the end. X cubed plus y cubed equal to 4xy plus 1 to have a vertical tangent. The denominator of dy dx must equal 0, and the reason why is as the change in x must be 0. That is what dx is. Okay, so if we do this, I'm going to set the denominator equal to 0. If this says in terms of y, what you're doing is you're just solving for x. So you have everything with y's in it instead. So I'm going to say negative 4x is equal to 3y squared. X is equal to negative 3/4. I'm dividing on both sides. Y squared. I just did this. This is it. You don't have to find any numbers, nothing else. It's just anywhere where x is equal to negative 3/4 y squared. I wouldn't quite say easy peasy lemon squeezy because, you know, there's difficult things on here. And by the way, this is another good one to just have out if you want to be more popular. But if you don't want to be more popular, make sure that you're shielding your work from others. So I wouldn't say easy peasy lemon squeezy, but I'm hoping it's not difficult, lemon difficult. The other common phrase. Okay, so moving on kind of to something a little bit different. This says, given the curve of y squared plus 2y is equal to 2x plus 1, and you have a little bit of experience with this already, but this notation, this d with an exponent of 2 and the y and dx squared, this doesn't actually mean an exponent of 2, it just means the second derivative. Why did they put the 2 within d and y in the first one and then not in the bottom? I don't know. But either way, this is where we're going to go with. This is the notation. Same thing over here. The second derivative, meaning you find the derivative and then you find it again. So let's do that. I feel like I should change to, oh, my chair is so squeaky. I feel like I should change to another color because this is slightly different than the ones above. So the derivative of y squared is going to be 2y dx. So if you haven't done this yet, you should try it now. 2 dx. I'm hoping you're getting pretty good at this by now. The derivative of 2x is just 2. The derivative of 1 is 0. I'm going to solve, get dy dx by itself. So dy dx, 2y plus 2 over 2. I'm going to divide both sides. And this is where I take my no simplifying business and I throw it out the window because I actually think you should simplify if you're going to take the derivative again. So here I'm going to say dy dx is equal to 2 over 2y plus 1 if I factored that out. So I really just have 1 over y plus 1. There are a couple ways that you could do this. You could use the quotient rule, which would be fun because we haven't done that yet. Bottom times the derivative of top minus top derivative of bottom over bottom squared. Or you could say, you know what? 1 over y plus 1 is just this. So I'm rewriting it, and now I can use the chain rule. Let's do that. So the second derivative, so if I take dy dx, so all of this was equal to this side. So this is my left side of my equation, this is my right. The derivative of dy dx is the second derivative. And that's all you have to do there. It's just the derivative of dy dx is the second derivative. Over here, I'm going to take my derivative and I'm going to use the chain rule because there's a function within a function. Wow. Do you like how my eyebrows really go? Like they get into the sound. Like it's like, wow, wow. Sorry, I forgot the B. That's not good. But like my whole face really gets into that. And I feel like that's really the correct way to do this. So really with emotion. Wow. When you're using the chain rule. Take the derivative of the outside. Negative 1. So I multiplied by negative 1. My new exponent is negative 2. Leave the inside alone. Times the derivative of the inside. What? What is this? Okay, let's keep going with it. I'm going to simplify this a little. I'm going to say -1 is in my numerator and my denominator to have y plus 1 squared. But then dy dx, I don't want to leave that in my problem, and I can't solve for it because there's a d squared of y over dx squared. Like, this is the second derivative. I can't solve for that, but I do know dy dx was just equal to this. Or I could say this one, but I already simplified a little bit. So dy dx was 1 over y plus 1. What? This is awesome. If I multiply the numerators and the denominator, I get -1 over y plus 1 cubed. That's very exciting. And all of this, by the way, just so it's really clear, was the derivative, the second derivative. Okay, let's do this one. It says, given this curve, the derivative of x squared is 2x plus 2y dy dx. The derivative of 1 is 0. Next, I want to solve for dy dx, so I'm going to get everything that doesn't have a dy dx to the other side. Divide by 2y, divide by 2y. So I get dy dx is equal to -x over y. The next thing that I do is I take the derivative again. The derivative of this side of dy dx is just the second derivative. So I'm going to write d squared y over dx squared. On the right, okay, here's where we get to use the quotient rule. What is the quotient rule again? Bottom times the derivative of the top minus the top. The derivative of the bottom, the derivative of y, is dy dx. Okay, over the bottom squared. Be really careful with your negatives and parentheses. I am so popular, getting lots of emails. Okay, the next thing I want you to do is, you don't have to simplify this too much. I'm just rewriting it just because y times -1 seems just obvious, right? As -y plus x, but instead of dy dx we knew was this. We knew it was the -x over y. So I'm going to bring this down here and I'm going to say -x over y over y squared. I would definitely recommend if you were doing a test and this were on a free response, for instance, leave the derivative like this. You can substitute it in x and y easily this way. It would be no problem. If this were a multiple choice question, you might have to get into one where there wasn't a -xy in the numerator. And so the way that you do this, oh my goodness, my chair is so squeaky, is you want to get rid of this y here. So I'd actually want to multiply everything in the numerator by y, everything in the denominator by y, so it's multiplied by some weird form of 1. And what you would get is -y squared plus this y would cancel out with this one, so it would be, I said plus, but then that's going to be a -x squared. So you could have just said -x squared over y cubed. And that's it. This is the second derivative. I can even put equals, I don't even need an arrow. Okay, and if you saw at the beginning, it says daily lesson 104 plus bonus page. Yes, but here's where you should actually just get out a page and you're going to write some stuff down. There's one more thing, one more differentiation that we haven't done. And so I think, I know in the progress track you saw one of these, but anytime we've done this so far, you've been able to use your calculator to find the derivative of x raised to an x. So this is a variable raised to a variable, and it looks crazy. But now that you know how to do implicit differentiation and natural logs and some other things, you actually can do this one. Like, no problem. We can figure out how to differentiate something that looks like this. Remember, differentiation just means find the derivative. So if I were to do this and I say, you know what, I'm going to take the derivative, if you ever see this notation, it just means the derivative of the left side, the derivative of the right side. And so a couple things that I want to show you. If I take the derivative of y, I get Actually, do I even want to do this yet? I want to do one more thing. I want to take the derivative of y, but before I take the derivative of x to the x, I just want to rewrite this. I want to say, you know what? What's another way that I can do this? Well, I should have stopped a little bit sooner. You know what? Okay, I'm going to cut this video part out of this. Hold on. It'll be fine. Okay. And, okay, so at the very beginning of this, I promised daily lessons, I don't even have it anymore, 104, but I said plus a bonus page. And so now I feel like I really need to give you that bonus page. I can't even find that one, but I need to give you that bonus page. And so what we're going to do is we're going to differentiate one more type of function. So you're going to learn one more rule, but this one you can always work through and figure out how exactly do I take the derivative of this. So differentiate just means take the derivative of x to the x. What? That's crazy. Up until this point, you've been able to use your calculator on any one of these. There's going to be some times when you can't. So what I want to do is I'm just going to actually rewrite this. So this is x to the x, but I'm going to rewrite this to something that you might know. So I'm going to differentiate both sides now that we know how to do implicit differentiation. I said differentiate both sides. Now I'm going to rewrite both sides. So I'm going to take the natural log of this side, the natural log of this side. And the reason why I did that is because now I can rewrite the right side into something that I know. Because natural logs, if you have an exponent, you can always take that exponent to the front and rewrite it as x natural log of x. Now this becomes a much easier problem. The derivative of natural log of y. Well, the derivative of natural log of anything is 1 over the anything times the derivative of the anything, or in this case, 1 dy dx. On the right-hand side, we just have a product. So we've got first times the derivative of the second. The derivative of natural log of x is 1 over x plus the second times the derivative of the first. Okay, this isn't so bad at all. So we've got dy dx. If we were to solve for this, dy dx is equal to, I'm going to multiply both sides by y. X over x would just be 1 plus natural log of x. But if I'm multiplying both sides, multiply this side by y, I should say y, and multiply this side by y. You're like, this doesn't look right. Give me one more second. Dy dx would be 1 plus the natural log of x. But remember, y was just x to the x. Pretty tricky, right? And also awesome. So you can do this even if there was natural log of 5x or something else. You just have to remember to also include the chain rule and use that as needed. Okay, there is a YouTube video that I used for this one because yeah, it just was really well explained. It was called the black pen, red pen derivative of x to the x. So if you don't understand this one, you could go on and watch this there. There's also another way that we can do this, that if we say, well, I know e to the ln of x is equal to x, there's another way that we can do this. You can kind of see my work. But we still end up with the same answer. So I'm just going to go with the one where we take the natural log of both sides. We did it, we did it, we did it, we did it. And by we did it, I mean you did it. Woo! I guess we did it because I did this part. Thanks so much for listening, for watching, for working, for asking me questions when you have them. Hint, hint, ask me questions when you have them. I appreciate you. I'm thankful for you. Great job being you. Thanks. Bye.